Is a wave always in the form of a sine wave? Why are electrical signals sometimes in the form of square waves? Why is music not made of just sine waves? A wave can take different forms depending on the force that generates it. While studying the wave mechanism, we always considered the situation where this force is applied instantaneously and no other force acts on the system, resulting in the fundamental oscillation, the sine wave. Therefore, a wave has another property: waveform. The waveform is the time-dependent change in wave amplitude caused by the time-varying force that creates the wave. In this video, we will capture this feature of the wave, mathematically derive the waveform depending on the variable force, and use the Fourier series to analyze it. Good luck to you all. A waveform describes how the amplitude of the wave changes over time. This change is due to the time variation of oscillations. Since oscillations are caused by time varying, in other words, periodic forces, for example, the restoring force in a spring depending on the mass position varying with a basic sine function, the oscillation changes over time accordingly. The most basic waveform is the sine wave. Other natural waveforms include square waves, sawtooth waves, triangle waves, or even chaotic non-periodic waves. Now we know that the thing forming the waveform is the force. To predict the waveform, let's apply a different force during the oscillation, not a sine function, but another function like f of t. The wave equation is the mathematical expression determining the motion of the system. Since the force affects the system's motion, it must be included in the wave equation. We add it as the force applied to a unit mass in the wave-producing system, which we can find by dividing the force by mass density. Fourier proposed that if a function is periodic, repeats over a given time interval, it can always be expressed as a sum of sine and cosine components. This is called the Fourier series. This means, even if a wave seems to oscillate in a complex way, it is actually the sum of simple vibrations, sine and cosine, at different frequencies. Each sine component acts like a mode, natural vibration shape of the system. When a complex force is applied, the system responds to each component individually. The resulting wave is the sum of all responses. If the sum of different amplitudes creates a periodic function, it can be mathematically expressed like this. Or it can also be written as each coefficient, a sub n and b sub n, shows how strongly the system responds to the nth frequency component. The expression omega sub n, denoting the nth frequency, is an integer multiple of the fundamental frequency. To find these constants, multiplications and integrals are used. To find the constant a0, isolate a0 and take the average value integral over one period. Since a0 is not time-dependent, it comes out of the integral. The sine and cosine integrals on the right are 0. Thus, we get the following equality. To find the values am and bm, we use similar methods. For am, multiply the equation by cosine with mth frequency and integrate over one period. We apply the same for bm. With these expressions, we can find all the constants. But since we want to find the function itself, you may ask how we get the constants. For this, non-sinusoidal periodic waves are expressed using piecewise functions. For example, let's consider square waves commonly seen in electronic circuits. Square waves are expressed as a piecewise function like this. Now let's use this function in our equalities and find the Fourier series expansion. First, find the fundamental frequency using the period of the square wave. Now let's find the constant a0. The constant a0 shows the average value of the function and physically represents the average effect of the force on the wave. We find it to be 0 because the square wave oscillates between -1 and 1, so its average is 0. Now let's find the constant a sub n. The constant an depends on the cosine function, which is an even function. If the piecewise function includes even terms, this coefficient is non-zero. In our square wave example, the function has odd symmetry around the origin, so it is an odd function and a n is 0. Now let's find bn. The constant bn depends on the sine function, which is an odd function. If the piecewise function is also odd, this term is non-zero. In our example, it is odd, so we get a non-zero coefficient. Now substitute into the Fourier series. The term sin of n pi divided by 2 squared equals 1 only when n is an odd integer and 0 otherwise. Therefore, we can rewrite the series as. Thus, the square wave in our example is expressed as the sum of infinite sine waves, which are fundamental periodic functions. Thanks to the Fourier series, any periodic function can be expanded into a series. So how do we use the Fourier series in wave mechanics? We answer that here. We mentioned a forced wave equation at the beginning. The function fxt on the right side represents an external force applied to the system. If the force were sinusoidal, solving the equation would be easy since sine waves are natural solutions. But what if fxt is a square wave or another piecewise function? Here's where the Fourier series comes in. We can express the complex function fxt as the sum of sine components at various frequencies. This is the time-domain Fourier expansion of a square wave, position-independent forcing. Now substitute this entire expression into the wave equation. Since the system is forced by sine components, we can write a separate solution for each nth frequency. Each y and x is the spatial solution showing how the wave responds at that frequency. This function can be found by plugging it into the equation. Because the differential equation is linear, such superposition solutions are valid. As a result, we can solve the forced wave equation using the Fourier series. As we see in this example, the real power of the Fourier series lies in this. When a complex force is decomposed into sine, cosine components, the wave or vibration system responds to each component individually and easily. The system's total response is simply the sum of all these responses. This is not just a mathematical convenience. It expresses a physical truth about how waves behave in modes in nature. Now we can examine not just the form of a wave, but also the frequencies hidden in the force shaping it. Every complex wave we observe in nature is actually made of regular, familiar oscillations, like notes in an orchestra. With this understanding, we can now not only analyze vibrations, but also hunt waves. In our next video, we will explore how to solve wave mechanics under non-periodic forces using the Fourier series. Remember, everything comes from science.